Right. Today I have a record video for recover for my Thursday due to I'm going to conference. So just we'll try to solve the example one for chapter 4.1 about the topic spectrum of a power spectral density of the band the path signal. Okay. I'm going to skip more detailed theory because we have already done. But please review my previous slide and the reader books. Okay. All right. So the first questions, we have to read first. So the AM voltage signal, okay, the AM is amplitude modulation, okay, the amplitude modulation signal that was S of t with a carrier frequency that was 1 kilohertz that was given, has complex envelope is G of t that was given the mapping function for AM signal, A sub C of 1 plus M over T, A sub C is what? Is voltage amplitude, the peak value is 2 voltage. And modulation is at what 10 hertz. Sinusoid tone described about M over T. One amplitude value, the time sine over 2 pi, the 10t. All right. All right. So first question is, what is the voltage spectrum for the AM signal? Okay. We might have to be two steps. The two step. The first over, this is one. Okay. So M over T, that was the given sine 2 pi ft. We can rewriting for trigonometric methods like this one to j e to j 2 pi 10 t minus to j minus 2 pi the 10 t. 1 over 2j, the Fourier transform. You can check in the table the delta function f minus 10 minus delta f plus 10. Okay, this is Fourier transform of the m of t. This is first step. Okay, now we have to also find the spectrum of AM signal, the G of t. That spectrum is for the S of F. We have learned before spectrum the A of F, that was the A sub C, delta F minus F sub C plus M F minus F sub C plus delta of F plus F sub C F plus F sub C. So now, maybe again, I do not have the repeat again for the definition, or I do not skip. I mean, I'm going to skip to the make a derivation. Okay. So you have to go back to my slides and my books. So please read first. Okay. So we are to, for example, from the questions, the F sub C, the is what? I'm going back to here. Let's see. G of T, right? Oops, right there. This is the two ball, right? And the F sub C is 1000. Okay, the carrier frequency, the AM, the carrier frequency. Okay, so the A sub C is the two ball, and then the carrier frequency is what? 1000. So right there, 2 over 2 delta F minus 1000 plus M of F minus 1000 plus delta F plus 1000 plus M of F plus 1000. Okay, all right. So that was one. All right. So that is the answer for the question one. I'm gonna just the other color, this one. Okay. So that is the answer for the voltage spectrum of the oops, the AM signal. All right. So now the question two. Um, Oh, by the way, I have a missing. Oh, okay. We needed, I'm sorry. We needed one more step, right? I'm gonna do another color. So M of F, we have to put inside and put inside. So that was what? Delta F minus 1000 plus 1 over 2J. Delta is what? F minus 1000 minus 10 and minus delta F minus 1000 plus 10, right? Um, and also the plus delta F plus 1000 and plus 1 over 2J, um, F plus 1000 minus 110 minus plus 1000 plus 10, right? So in here, we have the last 1000, 1 over 2J, the delta F minus 1010 minus 2J over delta F minus here plus F plus 1000 and plus 2J delta of F plus F minus 2J delta of F plus 1000, the 10. Yes, that is for the what we wanted to do, the answer. Okay, sorry about that. This is what we want to do. All right. So the question two, just the black one. Okay, black one. We have to looking for the compute for the PSD, power spectral density for the AM signal. So in the previous slides, we learned about the power spectral density could be indirectly method acquired by the autocorrelation of Fourier transform. Okay, so I I wanted to very quickly for reminder for your definitions, maybe sky color. Okay, this definition one. So if 0 is the angular frequency to pi f sub 0, right? And the m of t is a times sine omega 0 sub t. Just we assume that here. So indirect method of the PSD. The r sub m of the tau is the m of t, m of the t plus 1 tau. Um, that was what? This is the time average the maybe operator here. So limit t is the infinity 1 over t, the t over 2 minus t over 2, the 8 squared sine omega sub 0 t sine omega 0 t plus the tau dt. Okay, so in here we know it's like the trigonal matrix. Oops, I'm sorry, it's right there. Here, the 2 sine x sine y and then cosine x minus y minus cosine x plus y. Yep, that is what we wanted to do. All right. Um, so the, in here, the infinity 1 over t, t over 2 and minus t over 2. Okay. So that was 1 over 2. Okay. So cosine uh, minus tau minus cosine x plus y to the tau. Right. Okay. So that was for the dt. And we learned before that was the integral periodic sinus waveform is going to 0. And the cosine minus tau is cosine 0 to tau. That is the constant because that was not the function the base on the t. So it means you got the I'm gonna just put one here. Let's say maybe 8 squared over 2 cosine tau limit t is going to infinity 1 over t, t over 2, t over minus 2, 1 dt. Yes, that was for what? It's 1. So finally, 8 squared over 2 cosine omega sub 0 tau. That is for, is what? The autocorrelation to for the input value. All right, so wrong way. Okay, so means r sub m over tau is 8 squared over 2 cosine sub 0 to tau. So we can also, that was 8 squared over 2, 2 over e to j omega sub 0 tau plus e to minus j omega sub 0 to tau. Um, so now, but from the questions, from the questions, it was given A is what? It's like 2 voltage, and W sub 0, that was 2 pi 10, right? So um, we are finally r sub m over the tau, 2 to 4, multiplied to e to j, 2 pi 10 tau plus e to minus j, 2 pi 10 tau. Okay, so that was our value. And 2, like this one, right? Okay, now from the previous slide, we learn about the uh, okay, in the here. Okay, oops, something wrong. No. Oh, okay, that was not two, just right now. Oh, this one too, but that was for. Just give me a second. Um, uh, oops. So M over T. Oh, that was the one. I'm sorry, that was the one. I have to remove here. That was 1 square. Sorry. So it means that was this one because from the M over T. Okay. So in here, that was what? 1 over 4 e to j 2 pi the 10 tau plus e to minus j 2 pi 10 tau. So Fourier transform, so Fourier transform means that was a piece of M of f, our spectral density, 4 over 1, delta f minus 10 plus f plus 10. Okay. That was what? That was the PSD of the M over T. All right. Um, now, okay. Now, now you needed to we needed to um the next one is we try to autocorrelation for complex the envelope, the autocorrelation for the complex envelope of the AM signal. For this case, what we wanted to do. So in direct method, the autocorrelation, we have to find R sub G over tau. There was autocorrelation of the AM signal. Oops, sorry, this is delete. Okay, so in here, there was what? This is the complex. So this is why we have to conjugate here, T plus tau. Here we go. Uh, and that is what we have already over t the mapping of the function for AM signal that was given from the questions. So a sub c square 1 plus m over t and 1 plus m over t plus tau. Just calculation. A sub c square 1 m over t. Oops. M over t plus tau and m over t plus tau. Yeah, that is what you need to do. That is what you need to do. Um, but in here, um, let's say the m over t is going to 0. We learned before in the class. And also m over t plus tau is going to no autocorrelation. It's going to 0. But in here is 1. That was keep staying here. So finally, the c square 1 plus m over t, m over t plus tau. Okay. All right. So that is what? That was r sub m over tau plus 1 dA sub c squared. That was finally r sub g e of the tau. Okay. All right. Okay. So that is also what we needed to do for the future. Um, for the future, the calculations, we needed to one more things, definition as well, just to remind of you. Um, uh, from the books we learned before, the PSD of the waveform V of f, the p sub over f is the equal to 1 over 4, p sub g of f minus f sub c, plus p sub g f plus the f sub c. Okay. Um, and also, this is that we learned before, just to remind of you, if we wanted to the Fourier transform of r sub g over tau, the autocorrelations, you know, what is it? P sub g of f is what? A sub c squared delta of f and a sub c squared p sub m of f. Okay, this is particle density of the modulating signal. We have learned before in the slide. Okay, you can check. In here from the questions, the given the a sub c is the 2. Okay, that was the given. Go back to here, maybe. Just give me a second. Yep, slide 2 here. Um, so for f, for p sub m of f. Okay, so means for f, what is the p sub m of f? So what is it? Um, P sub m of f, we learned before in the previous, where is it? It's right there. Oops. The 1 over 4, 1 over 4 times 1 over 4, delta of f minus 10 plus delta f plus 10. Okay. Oops, right there. Here we go. Yeah. Okay. So we're gonna rewriting for delta of f plus delta f minus 10 plus 4 delta of f plus 10. So that is for what? P sub g of f. Okay. Okay. Now, um, so the finally the question is the power spectral density for the AM signal, right? So that means we need looking for, I'm gonna just writing for you, PSD for the AM signal we learned before. That is what? the piece of of f. Okay, so piece of the scope of f is 1/4. 1/4 is what? Piece of g f minus f sub c plus piece of g minus f sub c. Okay, so the carrier frequency, go back to here. Back to here. 1 kilohertz, right? 1 kilohertz. So as I understood, that was 1/4 piece of g f minus 1000 plus piece of g minus f. Okay, I'm sorry, but I'm missing minus 1000. All right. So what is the piece of g? Just AM single spectrum. Go back to here. Um, backside right there. So so step by step. Let's say. All right. So how can I the writing for? Okay. Delta f minus 1000. Okay. 1/4. Yeah, sure. Oh, it was wrong right there. Right? Just some calculation. Sorry. 1/4 f minus 1000 minus 10, and then the 1/4 f minus 1000 to plus 10. Okay. And also see the 1/4 delta minus f minus 1000 plus 1/4 minus f minus 1000 minus 10 plus 1/4 minus 1000 minus 10. So finally, that was f minus 1000 plus 1/4 delta. Okay. And then the 1/4 of delta f minus there, delta minus f minus 1000 plus 1/4 delta of minus f minus 1000, 1/4 delta minus f minus 990. That was piece of f. It's really long and the answer. All right. Okay. The question, go back to here. So the question 3, assume that AM voltage signal across the 50 ohm resistive with the road, compute the the average power dissipated in the road. Okay, so we have to normalize power first, and then we're gonna apply for this one. So, okay, what is the question number? Number 3. Okay, the first over normalize the average power. From the lecture, we learned before the normalize usually the R is equal to 1. Okay, so as normalize the RMS, same as square 1 over so m square the RMS. Again, that was this formula from the equation from our previous lecture. You can check. And I'm gonna just write one. That was what? It's 1. So that was also square the RMS. Okay. So that was what is the piece of m? So go back to here. Um, this is 1. Oops, this is 1. So the RMS value should be 1 over root 2. Okay. 1 over 2. And a sub c square, 2 square, 1 plus 1 over root 2 square. And then 2 times 1 over 1 over 2. 2 times 3 over 2. 3. Okay. All right. So that is for the piece of as the normalized, but we needed to looking for the actual value. Okay, so how can we find the actual value? The actual value is simple one because you know um piece of s, the actual value, that was what we wanted to do. Piece of s square RMS S of L square over 5 ohm, 9 over 5, 1.8. What? Okay, that is the answer. All right, so what is question 4? And that is the we are looking for is what? The peak envelope, the power. Okay, peak envelope, the power. PP. Okay. Um, so PP, this is also normalized value. We learned before in the previous the lecture that was 1 over 2 max the G over T square, 1 over 2 the A sub C square, 1 plus max M over T square. Because why? Because the G over T is the maybe other part is always constant. Just the message signal is like function. So that is why the maximum value is only related to the M over T. So that is why we have only max right there. The 1 over 2 times 2 squared, 1 plus. What is the M over T is like maximum value. Just like the peak voltage. What is the peak voltage? That was 1 square, 2 times 4, the 8 watt. Okay. So P sub PEP, the actual value, P sub PEP, Y's divided R sub L. The question is 5 ohm, right? Sorry, the 50 ohm. 50 ohm. There's the questions. I'm going back to here. Oh, not 5 ohm. Okay, that was we're gonna be assume that 5 ohm. Okay, this is the 50 ohm. So 50 ohm right there. Oops, 50 ohm. The 8 watt. That was what? 100. So that is the answer for the actual peak, the envelope, the power. Okay. All right. Thank you.